In this video, we will go through an example of determining load paths and load flow using this sort of simple structure here. And we're going to say that it's an occupancy of an office. It's a 9 meter by 9 meter square with 4 columns in the corner. The columns are 100 by 100 by 6 square hollow section steel units. The secondary beams are 360 UBs by 44.7, so universal beams, so steel beams there. We have joists, which are 230 by 45, spanning in this direction, and there's a 21 millimeter thick plywood sheathing over the entire area. So the two external secondary beams are these 360 UB by 44.7. The internal secondary beam and the two girders, or if you like primary beams, all three of these are 360 UBs by 56.7. So what we want to do is sort of determine some loads on here, and I've gone through and I've done a load takeoff based upon the unit weights of the members. So with the steel members, what's useful is the second number here is the weight in kilograms per linear meter. But we're going to need to find out, well, what the weights of the plywood and the timber joists are going to be so that we can then trace the loads all the way through the structure. So having done that, sort of before starting here, we've got unit weight of timber, and then I'm getting these numbers primarily out of the New Zealand loading standards 1170.1, and you can see the references here on the side. So table A1, and then we'll have another table there for the live load. But you can see the unit weights of the timber, 4.6 kilonewtons per meter cubed. That's for Pinus radiata. And so if we want to find out, well, what the weight of our joists are per linear meter, we can just take the area and then multiply by 1 meter, obviously. And then we can multiply by the unit weight, and we find that the joists are 0.05 kilonewtons per meter. Similarly with the plywood sheathing, we can pick out that for, again, coming out of 1170.1, per 10 millimeters of thickness, we get a unit weight of 0.12 kilonewtons per meter squared, or kPa. And then so if we divide 21 by that and sort of essentially multiply this out, we get that the plywood is going to weigh 0.25 kPa. And that's the force that'll be on there. Some other loads that we have, obviously, in buildings we have the finishes and services and the like, so we'll take some allowance for that, for the carpet, for the drywall ceiling, so the gypsum board ceiling, for the, any mechanical, electrical, plumbing would take just a small amount of weight for that. That's typically not a heavy load, so 0.01 kPa is appropriate. And we'll throw some sort of miscellaneous on there as well, just for anything we might have missed. And then if you add up all of your total superimposed dead load, so the superimposed part, this is anything other than the self-weight of the structure that is permanent to the structure. That's going to be 0.16 kPa. Now, we build buildings so that we can occupy them and, put people and furniture and the like in there. And so we need some live load. In New Zealand here, we use for our imposed load, we use Q as our sort of letter of choice. And same thing for dead load here. We use G for the permanent load. And so our office live load for this occupancy is going to be 3 kPa, and again, that's just coming straight out of the loading standard. So now that we have kind of all of the loads, and we see the joist spanning this way, well, what we want to do is chase the loads from the plywood sheathing to the joists, to the beams, and then to the girders, and then into each of the columns. So that's what we're going to step through here. We're going to use, just kind of work through. And this is, as I said, very similar to what you would do for calculating these loads for a building. So first thing we want to start with is, and we'll just put a little reference column up here, is the sheathing. So with the sheathing, let's just draw ourselves a little bit of a sketch here. So, and what we'll do is I'll draw kind of right here in this area, just so we can get a good picture in our heads about how all of this looks physically, and then we can use that to figure out what our forces are going to be and what our loads are going to be. So I've got the girder on the exterior, and then I've got a series of joists, and I've got plywood sheathing over all of that. And these joists are going to be at 600 millimeters, typical spacing. And in fact, we'll put that up here on joists at 600 at 600, just so that we have it nice and clear there. So let's say these joists are at 600 spacing, and then we've got our 21 millimeter plywood sheathing, and there's some applied uniform load from our live load and our superimposed dead load going all the way around this big uniform load. And so what we want to do is find out, well, how much of this uniform load goes to a single joist, how much goes to the girder, just from the sheathing and the applied load. But before we do that, just a sort of point of note is that we're going to make some simplifications as we analyze this. And these simplifications are useful in design because when working with buildings, we're going to have uncertainties in material properties, uncertainties in the construction quality, and so we would rather, and then because the design is going to be iterative, we'll have to do these calculations over and over again until we come up with an optimal solution. It actually doesn't make a lot of sense to get really too precise in our calculations, and so we have to have sort of an acceptable level of crudeness with this, and as long as those simplifications are conservative, that's just fine for our design. So the first one is, if we look at sort of the actual free body diagram of the sheathing. And so I'll just draw out a small portion of it. So this is our sheathing. We have some uniform load on it. And then we have these series of point loads. And so our deflected shape for this is, again, if I just draw it like that, we've got our point loads coming up. Because our sheathing is continuous, our deflected shape is going to be something like that, which means that we will have both positive and negative bending moments in the sheathing. But that gets kind of, confusing, difficult to analyze. And so, because we've got these negative moments, that actually helps reduce our deflection. So instead, what we will do is we'll assume internal pins at each joint. And we will just analyze the sheathing as if it were simply supported. This is a conservative way because it will have larger bending moments, it will have larger deflections, and it's much quicker to analyze. So that's the assumption that we use as structural engineers. So assuming internal pins, and we'll just assume an internal pin every place we have a reaction. Just like that. And so that means that we have a deflected shape that looks like this, where it's just like it's simply supported. And then we have our value W. All right, well, I think we are actually ready to start doing some calculations and working out, well, what our demands on the sheathing are from our live load and the self-weight of the sheathing and the superimposed dead load. So what we're going to do is working out W, but because we want to deal with the uncertainty of our loading, we use load factors and load combinations. So the load factor and load combinations we are going to use are 1.2 G, so 1.2 times the dead load, plus 1.5 Q. And then just to write this out explicitly, that's going to be 1.2 times the superimposed dead load plus the self-weight of the sheathing plus 1.5 times the live load. So that's a fairly straightforward calculation. We'll just sort of plug and chug with that. So if we do that, we get W equals 1.2 times our superimposed dead load, if we come back here, is 0.16 kPa. 16 kPa plus the self-weight of the sheathing we worked out, if we come plywood sheathing, 0.25 kPa. 5 kPa, and then we have to add 1.5 times the live load, again, which we worked out was just 3.0 kPa. And all of this is just coming off of page 1 of our calcs. So 3.0 kPa. And we'll call this W star. And we'll just use the star just to denote that we're working with factored loads. We get that equal to 4.992 kPa. And so we will just round that up to 5.0 kPa. All right, so the next thing we need to look at is, well, what is the load? So we know this is the applied load that the sheathing has to take. All right, so it has to take its self-weight and has to take these applied loads on top of it. Now let's see, well, what's the load that the sheathing applies to the elements which are supporting it? And so we'll start with the girder. So we'll go load onto girder. we'll just, actually, before we do that, we'll just draw everything out. Load onto girder and joist for a 1 meter length of sheathing. So what does our free body diagram look like there? Well, we'll have a reaction from the girder. We'll have a reaction from the joist. And then, again, the joist. And that'll just keep going. And then simply, if we've got 5 kPa and we're taking a 1 meter length, we'll just have a 5 kilonewton per meter uniform load. It's 5.0 kPa times 1 meter equals 5 kilonewtons per meter. And the spacing here, 0.6, 0.6. All right, well, if I want to find out what the reaction is on this girder, and remember, we're just going to assume internal hinges above each of these so that you can treat this like a simply supported structure. Well, if we're looking at the girder as a simply supported structure, that means that we have a free body diagram just like this. So a uniform load on a simply supported beam. We know that the reactions are just going to be the total load divided by 2. So that's it's pretty straightforward calculation. So we would have, so the reaction at the girder is simply going to be 0.6 meters times 5.0 kilonewtons per meter divided by 2 equals 1.5 kilonewtons per meter, and we'll call this W star floor girder, just because we will apply this load elsewhere. And we have R of the joists. Now remember, we've got one free body diagram that looks like this, one free body diagram that looks like this, so that means that we have essentially that much load coming into this joist, because you've got a reaction from this side and a reaction from this side. So we simply have 2 reactions times 0.6 meters, 5.0 kilonewton per meter divided by 2, 3.0 kilonewtons per meter. All right. So there we go. That's what our applied load onto the joists from the sheathing is going to be. So now what we need to do is work through, well, what loads do the joists have to withstand. So we'll come over here to our page 3, and again we'll keep our reference column over on the side. So working out the loads on the joists, let's draw a free body diagram of these joists. So they're timber, so we're going to analyze them as simply supported. Just going back to our little framing plan, we can see that the joists are spanning in this direction. That's what these little arrows are showing. And they are 4.5 meters long. So and at one end, we would have them at, beam C or beam A and beam B. And so the C and A is just coming from the grid lines that we have here. So the joists will either be spanning between grid lines C to B or A to B, and we can just do one analysis because this is a symmetric system, and so the reactions will just be mirrored. All right, so what are the loads which are applied to these joists? Well, every element has its own self-weight. And then, as we just worked out from our last page of calculations, we're going to have 3 kilonewtons per meter coming in from the sheathing. And we'll call this, let's actually just give this a name. We'll call this W floor J, W star floor J. W star floor J. All right, so again, we're still working with the same load case and combination of 1.2 G plus 1.5 Q. So we need to work out what the self-weight is, and we need to factor it. So W self-weight, that's just going to be 1.2 times the self-weight of the joist, which, again, we've already worked this out. We've worked out that it's 0.05 kilonewtons per meter. So times 0.05 kilonewtons per meter plus 1.5 times 0, because there is no live load for a self-weight. And so that we get W star self-weight is just going to equal 0.06 kilonewtons per meter. And then we already know that W star floor J is equal to 3.0 kilonewtons per meter. And that's because we worked that out on page 2. And as I said, that was just the calculation that we just finished up here. Also note that we've already accounted for this 1.2 plus 1.5 factor in the weight of the floor. And so we want to make sure that we don't accidentally plug that back into this load case, or we start double counting load. So now, again, we have a simply supported beam, and we just need to work out what our reactions are. So if we work out the reaction of beam A or beam C, so that's this side, so that'll be the reaction that the joist is putting in, for these joists over here, putting into beam C. For these joists here, the reaction putting on to beam A. And always keep in mind that the reason we're doing this is we're trying to trace loads down and see how they collect through the structure. So that's simply going to be 1/2 times 3.0 plus 0.06 kilonewtons per meter, so just adding up these two, multiplied by 4.5 meters, and then we get our beam, we'll do A/C, equals 6.89 kilonewtons. So fairly straightforward there. Now for beam B, again, we'll just draw a little picture just to make it clear since this is the first time we're doing this. So at beam B, we've got joist framing in from both sides. So our little picture there, we would have our beams. So we would have, grid line A, B, C. And then we've got joists coming in from both sides. That's 4.5 meters, 4.5 meters. And again, we've got this uniform load, primarily from the sheathing and the live load, pointing down on everything. And so that's just, again, showing a sort of a cross-section view. If I were to take a cut through this way and then look back that direction, you can see just like that. So, that's pretty straightforward. That means that we just have, we've got a symmetric beam here, so we know that both sides are going to have the same reaction. So on the beam at B, we just have to double this value here. So RB equals 2 times RA/C, and that's just going to be 2 times 6.89 kilonewtons. RB equals 13.8 kilonewtons. All right, well that's we're just progressing along quite well here. Now the next thing we have to look at are the beams. So we'll do page 4 here. And again, we'll just keep our reference column. Since we keep referring to loads that we've already calculated, it saves us having to calculate them again. All right, so the beams. So beam A or C. And just a reminder from this first page, they are 360 UB 44.7s. So we'll put some grid lines on here. We'll have our grid line 1 and our grid line 2. Again, just 1 and 2 there. And, we've got some loads. So we've got W self-weight. And then, we have essentially what are a whole series of point loads from all the joist framing in. So, if you think about, what we've drawn here, because our joist spacing is 600 millimeters, every 600 millimeters we have a reaction coming in from the joist. So that'll be 600 millimeters typical dimension. It'll be our column 1, R on column 2, and we're 9 meters long. All right, so the self-weight, well, we know it's 44 kilograms per linear meter. So we'll do W star self-weight equals 1.2. Again, we got to put that load factor on there. Times 44.7 kilograms times 9.81 meters per second squared. That gets us into newtons. And because we're working in kilonewtons, we'll divide by 1,000. Plus 1.5 times 0. W star self-weight equals 0.53 kilonewtons per meter. All right, very good. Now, the reaction from the beam here. So we'll say, actually, we'll put some label here. So this is, R beam AC, and that equals 6.89 kilonewtons. That's just all coming from page 3. So yeah, there you go. Each of these point loads is going to be 6.89, spaced 600 millimeters apart. But if you remember, as we've discussed previously, that when we have a lot of point loads, it's pretty easy to just simply simplify this down to a uniform load. So if we've got more than about four equally spaced point loads on a simply supported beam, let's just treat this as a distributed load. So I'll write this down. So, our beam equals many point loads equally spaced turn it into equivalent uniformly distributed load. So in order to do that, this 6.89 is already factored, so we don't have to do 1.2 times 1.5. All we need to do is, because we want something, a load, so some force per 1 meter, and we're at 600 millimeters. So all we need to do is divide this force by the spacing. So our beam equals 6.89 kilonewtons per 0.6 meters. You see that our units are lining up now, so it's 11.48 kilonewtons per meter, and then we'll just simplify that down. Our beam equals 11.5 kilonewtons per meter. All right, so now if we want to figure out what these reactions are, it's simply going to be these two uniform loads. And again, we'll do this R beam star just to make sure that we know these are already factored. Well, we just add these two uniform loads, multiply by the length, and then divide by 2 since everything is symmetric. So R column 1 equals R column 2, symmetric, so these are both going to be equal. That just equals half of the total load, 0.53 plus 11.5. times 9 meters. R column 1 equals R column 2 equals 54.1 kilonewtons. All right, so now let's look at, so we've done beams A and C. Let's do beam B. And just for reference, again, that's going to be a 360 UB 56.7, and that's just coming straight off of our little key plan here, our little drawing. So, again, we just draw the free body diagram, and we'll go put our grid lines on here between 1 and 2. We got W star self-weight, and then we have R beam, which is just going to be 2 times what we had applied here. So we've already worked out what this is as an equivalent uniformly distributed load. That's just going to be 2 times 11.5 equals 23 kilonewtons per meter, and that's because we've got joist framing in from both sides. Our column 1, our column 2, and again we are 9 meters long. So let's work out the self-weight. We've got a slightly bigger beam, so we've got to work out a new self-weight. Self-weight equals 1.2 for our load factor, 56.7 times 9.81 over 1,000 to get us into kilonewtons, and plus 1.5 times 0. And we find W self-weight is going to equal 0.62 kilonewtons per meter. All right, so now all we have to do is just work out what these reactions are. We know our load here, it's 23.0 kilonewtons per meter. And then we just need to add on our self-weight, multiply by the length, divide by 2 for each of these columns. So we've got, oh, actually, sorry, I've miswritten. Instead of the column, that's my fault there, we'll call this RG1 and RG2. And that's because this beam B is not supported by the columns, it's supported by the girders. And so this is going to come in as a point load here and here. So, apologize for that error as I'm going through here. RG1 equals RG2 equals 1/2 of two times W star joists plus W star self-weight times 9 meters, so that's going to be 1/2 times this R beam here. So we'd have 2 times 23 kilonewtons per meter plus 0.62 kilonewtons per meter times 9. RG1 equals RG2 equal to 106 kilonewtons. All right, so The only thing we have left to determine what our loads are our girders and our columns. So we're almost done. So, page 5. For the girders, and again, they're the same as that beam in the middle. It's a 360 UB 56.7. So, drawing our free body diagram here. Start at A, we'll go down to C. For our grid lines, for our girders, well, it has our column A, and then R at the column C. So this is RG, and that's equal to 106 kilonewtons. So we just found that, previous page right here. Previous page just right here. Well, we know we're going to have some self-weight. And then the last sort of uniform load that we have, if you remember, we've got some small load coming in from the sheathing. And that is because, I bring up the drawing there. If you remember, we have this little bit of sheathing load going into our girder over the whole length. So we need to account for that, as well as the self-weight, as well as this beam framing in here. So that's fine. This is just some accounting that we have to do. 4.5 meters, 4.5 meters. So we already know the self-weight because we just worked it out for the other beams, which weigh this much. So W star self-weight, 0.62 kilonewtons per meter. That's on page 4. W star sheathing is 1.5 kilonewtons per meter, and that's coming off of page 2. So as you can see, our girder 1.5 kilonewtons per meter, and RG equal to 106 kilonewtons, again coming from page 4. So pretty easy. We just need to sum these up and divide it by, sum the forces up and divide by 2, and that gives us our forces on our columns. So our column A equals our column C. Symmetric, so we just spread out the load by half. 106 kilonewtons plus 1.5 plus 0.62 kilonewtons per meter times 9 meters. And if we sum all of that up, we'd get our column A equals R column C equals 62.5 kilonewtons. All right, the final thing that we need to look at are the columns. So because we have a symmetric system here, where we don't have any openings, the framing's the same, we're the same dimensions in each way. That means that each of these columns will take essentially 1/4 of the load. And so, and because of that, we only have to do one calculation, and we know the loads on all of the columns. So for our columns, symmetric, structure, all columns, same load. So our column has a force column from the beam, and that equals 54.1 kilonewtons. It is a force R column from the girder, and that is 62.5 kilonewtons. Again, just what we found. We have the column, and then we have the reaction at the foundation. Summing forces in the Y, we get our foundation equals 54.1, 62.5. Foundation equals 116.6 kilonewtons. So that's coming off of page 4. And so that's it. So now what we've done is we've gone from sort of a plan and some understanding of the framing of our structure and what it's made of and what loads are on it. And we've chased the loads all the way from the sheathing to the joists, to the beams for both beams, to the girders, and then to the column. So we now know what every element within this, every element within this system, what forces and what demands it has on it. So that's essentially load tracing or load collation, where we're just going through and we're determining what these reactions are and what the loads are for each and every member. So I hope you found that informative and helpful. As I said, this is a technique that you use very commonly in structural engineering. And so with that, I want to say thanks for watching.